In this lecture, I am going to review question 9 and the question we're going to do in class today that you guys are missing. Any case, we're dealing with heats of fusion and vaporization problems and friends. This is the worksheet that I gave you, or you should have a hard copy of. All right, we worked on some in the lecture previously. Okay, so this is the heats of fusion, vaporization problems, and friends, and we worked through some of these with the previous lecture. Okay, I'm expecting that you've looked at your key and you reviewed some of these. I'm expecting you to have problem with number 9. Everything else I believe that you should be in good shape with. It's pretty straightforward. Understanding where you are on the heating and cooling curve and drawing yourself a thermal diagram and using the constants, heat of fusion, heat of vaporization. Number 9 is a little more detailed, and I want to walk you through this, and this is what I would have done in class because you took the PSATs. We're doing it now. Okay, so the first thing is to read our question here. 27 ice cube at negative 12.1 degrees Celsius. So this is key. We're below the freezing point or melting point of the ice cube. Is placed in a certain amount of water at 43.1 degrees Celsius. Okay, what will be the final temperature of the water once the ice cube has completely melted? A specific heat for the ice cube is 2.01. Now, interesting enough, the specific heat for water in a liquid state is 4.18 joules per gram per degree Celsius. Interesting enough, when it's an ice, it's lowered, which means its ability to conduct heat, okay, has changed as it becomes a solid. And you may say, well, why is that? And you can think with me, a crystalline structure like water, and I'll just draw the molecule of water like this. If it's in a crystalline structure, it's usually because it has strong intermolecular attractions. And now, of course, this is not a crystal of ice. But in any case, in the solid phase, you can only vibrate in your fixed positions. So if you think about this, the water is in a liquid state, okay, and there's a lot more range or degrees of freedom. They can spin, they can translate, they can move a lot more, although there are still attractive forces that keep them together as a liquid. We'll talk more about that tonight or the next day. When they're locked in a solid, they can vibrate only. So the ability to conduct heat actually increases as you become a solid in the case of water. Okay, because of these degrees of freedom and being so dense as a water, that as the density drops, okay, its ability to actually conduct heat actually increases. Okay, and if you were to move on this molecule, you'll affect these molecules more so than if you're in a liquid state for water and you try to move this one. Yes, there's attractive forces, but because there's so many degrees of freedom and so much motion, these don't cause the other ones to move as well. Therefore, the heat's not conducted as easily in a liquid state. In the solid phase, because they're locked in a fixed position, if I make this guy vibrate more with more motion, it'll cause this one to vibrate more. And because this one's connected to another one, you can see that heat is going to be conducted through the solid easier, and that's why its specific heat is less. It needs less energy to conduct heat because the conductance or the atoms are more connected. Here, if I vibrate this one more, okay, it has less effect on the surrounding molecules because they already have so much motion and they're not necessarily stuck in one position. So the transfer of energy is a lot harder because, well, this one's not really just here anymore. He's now moving here. So there is a conductance, but it takes a lot more energy because these guys are moving and they're not connected as well as a solid. So in any case, something to think about. So the specific heats of a solid, liquid, or gas in a heating and cooling curve will be different from what we're used to. So if you're dealing with a heating and cooling curve like I'm drawing here, in this case a heating curve, the solid, liquid, and the gas will have different specific heats. So when we do MC change in T, these C's will be different for the different phase. Even though they're the same substance, their ability to conduct is different, okay, as they are in their phases will limit or increase their ability to conduct. So something to think about there. Okay, so just because we have water, the specific heat of ice is needed. If I had the gas, it would be needed there as well. Okay, so let's get back to the problem. As I always say, draw yourself a thermal diagram. I've got an ice cube, so I'm going to draw this ice cube as best as I can, and it's in a certain amount of water. Okay, so we'll have it floating because it's less dense. Okay, and the water is at 43.1 degrees Celsius, and the ice cube is, we'll just put negative 12.1 up top since I probably can't fit it in there, degrees Celsius. Okay, we're looking for the final temperature of the water. Okay, we didn't talk about the cup, we didn't talk about any glassware, so the energy transfer we always have to assume is going to be just between the objects I talk about in this case, between the ice and the water. Okay, so clearly, okay, what's going to happen here is the ice cube is going to warm up and eventually it's going to melt, because once the ice cube has completely melted, we're answering this question, and it's very important you understand that designation. So once we have our thermal diagram and understanding the ice cube is going to absorb energy from its surrounding, it's an endothermic process, the water is going to get colder, okay, but we need to plot this on a heating curve to see what formulas we may need. So we're going to deal with ice below its melting point, and that's what I just drew here. Okay, and it's going to, we're going to figure out once the ice cube has completely melted, so it's going to be at this point. All right, so we're going to take ice below its melting point, let's say right there. It's going to hit its melting point and completely melt. So you probably can see what two things are going to happen here. First, we have to heat up the ice cube in order for it to melt, right? It's negative 12.1 degrees Celsius. We know it melts at standard pressure at 0 degrees Celsius. So we're going to need MC change of T. Why? Because there is a change of temperature, okay, and we have a pure phase. And then once we're here, once we get to the melting point, we're going to just need our mass times our heat of fusion formula to answer this. So the amount of energy that the ice is going to absorb to completely melt, and that's what this means. This should have said once has just completely melted. I probably should put that there. We're getting to that point right there. So this shows me the combined cumulative energy needed for the ice, or at least in its energy. Okay, and of course we're climbing the ladder, so this is endothermic. All right, so this is endo. So when we write our energy equation now, all right, we have Q of the ice equals Q of the water. Now, why does that work? Some people don't get this. This is conservation of energy, because we're going to say the energy absorbed, right? So the ice is absorbing energy. Again, the best word is consuming, but you'll see the word absorbing, and the water is releasing. The process is endothermic because the total environment's going down in temperature, because what's creating the energy imbalance is the ice cube. Okay, so Q of the ice. Well, just as I showed you here, the Q of ice has two parts to it. You have the what? The ice melting. I'm sorry, the ice warming, I should say. It's warming to its freezing point temperature or melting point temperature. And then we have the ice what? Ice melting. All right? And then of course we have the water, if you want to write this down, warming. Okay? So we have to think in terms of phase changes. Now when water warms, think about another heating or cooling curve. We know water, and I'm sorry, I shouldn't say water warming. My mistake, I'm adding an ice cube, so clearly water is cooling. All right. Well, you guys, Mr. Gratsky, yeah, I know. Water is cooling, okay? So, wouldn't be a lecture if I didn't have a mistake in there. In any case, water is cooling, so I'm starting at 40, let's say 3.1, It's pretty warm water, by the way, over 100 degrees Fahrenheit. Okay, and I'm going down some temperature change. Okay, and notice I'm on this line, so for water it's going to be MC change in T. So what we're going to have here is Q the ice equals Q the water, and now we're going to put the ice warming. So Q of the ice warming is going to be just MC change in T, okay, plus the ice melting, which is going to be what? The mass times heat of fusion. And of course, that's going to equal the water that's cooling, and because it's in a liquid phase and it's not having a phase change, we're using MC change in T. It's MC change in T. So I'm going to now plug these values in, and before we think about this, because the question was, what's the final temperature of the water? So I really shouldn't put the change in temperature, although, you know, I could solve for a change in temperature. I could put all these values in here and solve for change in temperature, right? And then I could subtract from 43.1. I could do that because I know it's going down. But I'll also do it the other way, okay? So that would be one way to do it. But I can also say, listen, I know that the final temperature is going to be lowered, so the initial temperature, 43.1, minus the final temperature. I'm just keeping this positive, okay? For those that are jumping in, I'm eliminating the negative values in my thermodynamic equations here. We would pick these up in an AP class. So I'm just keeping things positive here. All right, so in any case, you could have solved this. Let's put the values in and start simplifying, okay? Okay, so I just plugged in the values. This, of course, is the mass of the ice cube. Notice the mass of the ice cube, whether it's warming or melting, is going to be the same. And of course, we have the water cooling, and this is the mass of the water. Keep saying this, people keep making the mistake. We don't mix and match. This is the Q of the ice warming. This is the Q of the ice melting, and this is the Q of the water cooling. Okay, so they're always of the same substance. This is the mass of the water. Okay. Now you may say, Mr. Gradsky, okay, I got this, but some people might pick this up. At this point right here, when the ice cube completely melts, what's the temperature of the ice cube? You've got it. It's 0 degrees Celsius. What did I say in the problem? I said once the ice cube has completely melted, or just as it completely melted. So we don't care about that. But if you think with me for a second, if I said, what's the final temperature at the coldest possible final temperature, doesn't it make sense that this 0 degrees Celsius water, and it would be 27 grams of it, isn't it going to take energy away from the warmer water on top of it? So if I really wanted the coldest possible temperature, I have to consider not only the ice cube absorbing energy as it warms and as it melts, but also the water, okay, the liquid water that was once ice cube that's now 0 degrees Celsius, that will also absorb heat from the water. So there's really 3 things here. Now I eliminated that third thing because I said just as it melted, we stopped here. But really, if I said the lowest possible temperature, we have to consider the water that was once an ice cube that now is at 0. So you'd have 12.1 grams, 27 grams, okay, of water that's at 0 that will also absorb energy from the warmer water surrounding it. Now we eliminated that in this problem, but it's hint, 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 something to consider. So now let's go back to this problem and let's simplify, okay? And if you want to go simplify, you can pause this and I'm going to simplify. Okay, and 27 times 201 times 12.1 is 656.667 plus 27 times 334. You notice everything's going to cancel except for your joules. So you're really adding joules together, right? And of course the heat of fusion, grams go, and you got joules plus joules. In any case, same thing. 120 times 4.18 times 43.1 gives you this number. And then of course this times -1 or negative TF, it gives you this number. And now we are going to simplify further. -21618.96. Okay, that's going to cancel. and that becomes negative 21618.96. Okay, I do the math. I believe I get a negative 11944.293. Okay, this becomes, actually I added these two together. So this plus this minus this value. So these two blue numbers minus gives you that, and that equals a negative 501.6 TF. Okay, and of course we're solving for our final temperature. So all we got to do is divide by that. So TF is equal to a negative 11944.293 over negative 501.6. Okay, put that in your calculator. Okay, and TF, let's change it up because I can. TF is equal to 23.8. Okay, looking at my sig figs, looks like 2 sig figs. That became 120 grams, right? Density of water is 1, so it looks like 2 is my limiting factor. So my 23.8 becomes 24 degrees Celsius is my final temperature. Okay, and it's a good thing I didn't get, this didn't get any colder than 0 because then we have a phase change here. But in any case, that's the answer. And you know, of course, the math here is just the simplification. The chemistry or the physics is right here that I need you to understand, and especially this idea once the ice cube has completely melted. So that's the problem that I wanted to review with you, and the particulars of it. We're going to move now to the classwork of Heats of Fusion, Heat of Vaporization Problems and Friends 2. It's a worksheet that we're moving to now. Okay, so this is a more advanced problem, and we have a couple of different things we have here. If you look at the problem, what is the initial temperature of water if a 45.4 gram ice cube at temperature below its freezing point is completely melted in a 550 grams of water that achieves the coldest temperature? What do you think I'm talking about there? That must mean now I'm considering the water that was once the ice cube. Okay, a 24.3 grams styrofoam cup is used as the container. Now, something I want to talk about, the coldest temperature. Did we find the coldest possible temperature yesterday in lab? So in lab yesterday, okay, did we find the coldest possible temperature? And the answer is yes. We looked for the coldest possible temperature. Was this an error in our lab? Well, what did we say in our lab? We said Q of the ice equals Q of the water. But we were only considering what? We were trying to figure out the energy it took to do what? To completely what? Just melt the ice. So we were just trying to find this energy, the heat of fusion. But what did we do really? We found the coldest possible temperature. So what we had ice that was melting, and then what was once an ice cube, let's say you had a 10 gram ice cube that completely melted, that 10 gram ice cube was at what temperature once it completely melted? 0. So 10 grams of ice cube now is 10 grams of water at 0. And your water is what? Warmer than that. So not only did that 10 grams of ice cube melt, some of it, also warmed up. So what's our two formulas? So really, okay, in lab yesterday, we had the Q of the ice what? Q of the ice melting. And again, that was assuming we had ice at 0, right? What if our ice was below 0? So we'd have to warm it first. So we had Q of the ice melting. Let's assume it was at 0. But we did not consider Q of the what? Ice is now water that's warming. And that equals what? Q of the surrounding water. We didn't consider the water warming. So you think about it, didn't we measure extra energy? So our heat of fusion, would that be higher than normal? Should we calculate something greater than 334? Well, let's see. As a class, I asked you guys to respond as a class. So remember, we just wanted to measure this Q of the melting from here to here in our phase change diagram, or I should say my heating curve. But because we measured the coldest temperature, okay, we also had what was once an ice cube is now liquid water at what temperature? 0. So it's of course going to do what? Absorb energy from the surrounding water and make the water actually colder, okay, than it was supposed to be, since we looked for the coldest possible temperature. So extra energy was absorbed, therefore the heat of fusions should be all greater than normal. If our ice cubes are below 0, there'd be also some extra energy we added to heat them up to their melting point temperature first. Let's go see the data you collected, since I asked you all to respond in a form. Okay, so clearly, if you look carefully, okay, I have some people who responded in all lab tables, and we have 382, 345, 379, 360, 335, 357, 334, 370. Everybody is above 334. Okay, some more than others. We're close, but everybody's above. Nobody has a negative percent error. And the answer to that is because not only did we measure the melting of the ice, because we took the lowest possible temperature, we also measured what? We measured the amount of that water that was once ice, who's now at 0, warming up. So extra energy. So we measured the heat of fusion plus a little bit of water being warmed up by the surrounding water that was once an ice cube. So that should make sense to you. And it's a major error for your lab. Not enough to really make our heat of fusions be terrible, but consider that we weren't able to separate that melting. Now we could say, well, what was the temperature as soon as the ice cube melted? Then we would have gotten a better value. But still hard to do, okay? But we still got good data. Okay, so back to our problem. I'm going to set this up, and you can look over the key. I'm not going to, do the whole thing, and you can look at the key as far as a simplification. Let me set this up. So what do we have here? We have a container. In this case, we have they give me specific heat of the styrofoam, which is the cup. So we have to consider the cup part of our problem here too. So I'm going to draw my cup. Okay, and I have my water. And the temperature of the water is negative 10.3 degrees Celsius. And we have an ice cube. I'll draw that here. Not a great ice cube, but there's my ice cube. It's at negative 10 degrees Celsius. I think I have the water written there as negative 10. Feel bad. Okay, let's put back in the container. Now that I have a bigger container, I can redraw this. Sorry. So I got my container.
All seniors are to report to the cafeteria.
Okay, so here's my temperature of the ice cube. Okay, is negative 10.3 degrees Celsius. Temperature of the water is 21.3, and we can say that the cup and the water are in thermal equilibrium, so they'll be the same. All right, and we're going to look for the coldest possible temperature. So obviously the ice is going to absorb heat first to get to its what? To get to its melting point. So here's the first part. It's going to do that. So it's the ice and the water in the cup. So the two team players, who's absorbing? Okay, so we have heat absorbed versus heat released. Okay, now who's doing that? Okay, well, we have the ice, we have the Q of the ice warming, plus the Q of the ice melting plus the Q of the ice that's now going to be what? Water. So the Q of the ice that's now water heating up. Hard to say what it is. Heating. So I'm going to have something like this. So I have three equations. I have the MC change in T of the ice, specific heat of the ice. Then I have the mass times the heat of fusion of ice. And now I have water, MC change in T of the what? The water that was once ice. Okay, so this is going to be all the same mass. So the mass for my Q's are all going to be the same, which is 45.4 is going to be used in every single thermal equation because it's all the same. Mass doesn't change. Okay, who's releasing? Well, we have Q of the water plus Q of the cup. All right, the cup is also releasing heat as well. And we're looking for the coldest possible temperature. I gave you initials, so I'm looking for TF. Now, TF is going to be in the cup, in the water, and in this final temperature here. These values won't have a TF. Okay, so that's where TF is going to be. And you're going to do that. Okay, so please plug in those values. Please look over the key, okay, and see how I did that. Really, the setup of the problem is what you needed to see. Okay, because we're talking about the coldest possible temperature, what is new is we have to consider what? The extra heating done here due to the water that was once an ice cube. It's separate from this water. Okay, try that, look at the key, and I'll take any questions you have. All right, and that concludes what we've done in class that you missed that day.